Our next topic also involves solubility equilibria. We're going to talk about the effect of a common ion. So if we add a soluble salt that has an ion in common with an insoluble salt, we're going to, according to Le Chatelier's principle, drive the solubility of the insoluble salt backwards. It's going to decrease. So for instance, it's not working. If we compare adding some sodium chloride to this lead 2 chloride, we're going to shift our equilibrium back this way because we have extra of this and decrease the solubility of our lead 2 chloride. So let's look at an example. Determine the concentration of silver ions in seawater that has a chloride concentration of 0.55 molar. And we have the KSP there. So we know that our AgCl is in equilibrium with silver ions and chloride ions. We can set up our ICE table. Our initial of our chloride is 0.55 and no silver. We're going to gain some amount of silver. I'm just going to use an X because it's not really molar solubility. And gain some chloride because we don't have any silver there. It's just not going to shift as far. So X and 0.55 plus X. So our KSP, 1.77 times 10 to the minus 10 is equal to X times 0.55 plus X. That plus X is going to be very small, so we're going to ignore it. We're going to use that X is small assumption. And then we can solve for our X is going to be the 77 times 10 to the minus 10 divided by 0.55. So I get an X value of 3.22 times 10 to the minus 10 molar, which is very small. So there's that math worked out again. All right, back to pH. For some of these, changing the pH is going to change your position of the solubility equilibria. So if we have an insoluble ionic hydroxide, the higher the pH, the more hydroxide you're going to have around, the lower the solubility. And the lower the pH, the higher the solubility. And then for insoluble ionic compounds that contain anions of weak acids, specifically carbonate, the lower the pH, the higher the solubility, just like with the hydroxides. We can predict precipitation based on when the concentrations of ions exceed the solubility. So when we exceed our solubility, we will precipitate. So we can compare the reaction quotient Q, remember we talked about that way back in chapter 14, to the value of KSP and determine if our precipitation will occur. If they're equal to each other, our solution is saturated, we're not going to precipitate. If Q is less than KSP, the solution is unsaturated, so we're not going to precipitate. And if Q is greater than KSP, we're above the saturation point and the salt will precipitate. Now, there are some solutions that won't precipitate unless they're disturbed with Q greater than KSP. That's called supersaturated. Here's a slide showing what supersaturated solutions look like. So you can have a supersaturated solution of sodium acetate here, put in a single crystal, and it all precipitates all at once. Now we can selectively precipitate things. If a solution contains different cations, we could add a reagent that will form an insoluble salt with one of them but not the others. If something can precipitate with more than one we have to monitor the KSP values and make sure that we're only precipitating what we want. So let's look at an example. Will a precipitate form when we mix lead nitrate with sodium bromide if the concentrations after mixing are 0.0150 molar and 0.0350 molar respectively? All right, so if those are our concentrations, that means for our lead, we're going to have a concentration of the 0.0150. For our nitrate, we're going to have 2 times that, which is going to be 0.030. And for our sodium bromide, we're going to have a sodium of 0.0350 molar and our bromide of 0.0350 molar. Okay, and this is the equation we are curious about. We have to check our Q value, which remember we calculate the same as we do in R. It's going to be our lead times our bromide squared. We know our lead concentration is 0.0150 molar. Bromide is 0.0350 molar squared. So our Q value, if you do that math, is 1.84 times 10 to the minus 7th. We have our KSP value up here, 4.67 times 10 to the minus 6. So our Q is less than our KSP, so no precipitation. Here's that same thing all worked out. Here's another question for you to work through. A solution is made by mixing lead nitrate with silver nitrate, so both compounds have a concentration of 0.0010 molar. Sodium chloride is added to precipitate out both silver chloride and lead 2 chloride. What is the silver concentration when the lead just begins to precipitate? And we have selected solubility product constants. We're going to want to know our lead 2 chloride right here and our silver chloride right here. So, thinking about this, we are going to want to figure out our chloride So we're going to start with our lead 2 chloride. So we have our PbCl2 lead plus 2Cl minus. We want to find out when our lead concentration is 0.0010 molar, what our chloride concentration is at equilibrium. So we're looking for this. But remember so we're looking for that. And our KSP is going to be the lead times my chloride squared. I know my KSP is 1.17 times 10 to the minus 5th. That comes from the table a couple slides back, is equal to 0.0010 times my chloride concentration squared. So my chloride concentration when I'm at equilibrium here is 1.08 times 10 to the minus 1 molar. But the question asks me, what is the silver concentration when the lead just begins to precipitate? So now I'm going to go back to my silver, go to my silver. AgCl is in equilibrium with silver plus plus Cl minus. Now I can plug in my KSP, again from the table, is 1.77 times 10 to the minus 10, and that's going to be my silver concentration times my chloride concentration. I know my chloride concentration, I can plug that in. I know my KSP, and so I can solve and find that my silver concentration then is 1.6 times 10 to the minus 9th molar. So I just plugged my value in for my chloride when my lead started to precipitate, and I find that I only have 1.6 times 10 to the minus 9th molar silver left. By the time my lead begins to precipitate out, my silver has dropped from 0.0010 molar to 1.6 times 10 to the minus 9th, so it's dropped quite a bit. Here are the explanations. I skipped over this. This is figuring out when my silver starts to precipitate at this value of chloride. Then here's all of this math and this math. And that's it for that topic.